Okay, hello students and welcome to our last lesson on bivariate data analysis. We're going to be using that equation of the least squared lines today to make predictions, and some of those predictions involve interpolation and extrapolation, and there's going to be some dangers that you need to recognize about extrapolation. Then we're going to use this to solve some practical problems by identifying, analysing, and describing associations between two sorts of variables. So if we have a look at our scatter plot on the right, we've got a graph here with snow depth and number of skiers. So it's something that you might see on a holiday season at a ski resort. We've got some information here that it looks like a positive trend, and the dots are fairly close to the line. So there's a good correlation there. And the first skill I want to talk to you about is called extrapolation. And extrapolation involves making predictions beyond the bounds of the original data. So that's the extra or the outside bound, and here's the inside bound down here. So if you're going to make predictions then that are well beyond the bounds of the data, we're going to run into problems. So a question that would ask you to extrapolate would be, for example, how many skiers at a depth of 4.5 meters. This would require you to put in your line of best fit and then extend that line of best fit beyond the bounds of the data. And you'd may have to extend your graph here, and then you'd just draw that line up from your x-axis and read across to your y-axis, and so you would say, about 900. And that would be called extrapolating. Now, interpolation is making predictions within the bounds of the original data. So an example of this would be how many skiers at a depth of snow at 3 meters. So, well, we would just look at that and read up to that line of best fit, and then read across, and we could say, that's about 590 or even 600. And that's called interpolating. Now, the less data there is, and the further the least squared lines is from the original data, the less reliable the result. Okay, now we're going to have make some predictions between the latitude and the average maximum temperature. We're going to do this using the least squared equation. So what we'll do first of all is to get this data and just put it into a scatter plot, and that's what I've done on Excel. Now I've inserted the trend line, and I've asked it to spit out the equation, and I've also asked it to put in the r squared value for me. So Excel's doing a lot of the work here at the moment for me. I can see that it's a negative association too, can't I? So let's continue. So to work out the r value, remember it's the square root of the r squared. Now remember, if a negative times a negative is a positive. So if I look at the square root of something, it's either going to be positive or negative. That's why I've got the plus or minus sign there. You'd have to look at the graph and go, it's a negative relationship. We're going down from left to right. So the square root of 0.8282 is either positive 0.91 or negative 0.1. We've looked at the graph and said, okay, it's going down. It must be a negative relationship. Okay, or an association we could say as well. So we could say that there's a strong negative linear association. Now, reading from the r squared value, we can say 83% of the average maximum temperature responds to or can be explained by the distance south of the equator. Remember, this is our latitude south. So the further south we are going, the cooler it's getting. And that makes sense, doesn't it? Now, let's have a look at predicting Bundaberg and Darwin's temperature based on the degrees latitude. Well, we've got the formula nicely given to us from Excel, and we also have that r squared value. So there's that graph again from Excel with the formula and the r squared. And let's consider the reliability of the data. So first of all, Darwin, well, it lies well beyond the extreme values of the data. So where's Darwin? It's 12.46. So if that's 10, and that's 20. It's got to be there. So we're going to think, oh, we need to continue this line up here somewhere. What's that doing? So it's not being very nice for me. And there we go. So it's going to be up there somewhere, about 40 degrees by the looks. So let's just extrapolate this, and we'll note that it's going to be less reliable. So we'll substitute in those values from Darwin. So what did we say? We've said that Darwin is 12.46. So that's our x value, and that's where we're going to sub into that x value there into the equation. So y equals negative 6.134x plus 48.938. So we've just substituted that into the equation, and we've predicted that Darwin's mean maximum temperature for February, this is going to be 41.29 degrees Celsius. Now Bundaberg, it's pretty well 25 degrees south. So it's going to be somewhere about there, between 20 and 30. So you can see it's going to be predicted to be maybe 33. Let's have a look. We'll substitute this into the equation. So here's our x value, and we're just subbing it in instead of x. So it's negative 6.134 times 12.46 plus that 48.3. 48.938, and we've predicted it to be 33.68 degrees Celsius. Now let's consider the reliability of these predictions now that we've been given the actual values. So I looked up them on the BOM website and found that the actual mean monthly maximum temperature for Bundaberg is 30.1 degrees Celsius, and for Darwin it's only 31.5 degrees Celsius. So let's consider our residual values. So here's our x value, this is our YA, this is our YB. So we've just said that our residual value equals the actual value minus the predicted value, and we've got a residual of negative 9.79. So that's a fair discrepancy, isn't it? Now, if we have a look at Bundaberg, we've got an x value of 24.87. That's our degrees latitude, but we want to work out YA minus YB to get our residual value. So 30.1 minus 33.68, that will give us negative 3.58. Now this is expected, isn't it? So the mean, so as expected, the average maximum temperature for Bundaberg was predicted with less accuracy. Now that's due to extrapolating well beyond the domain of the given data. Are you able to use that equation of the least squared line to make predictions and consider the danger of extrapolating beyond the bounds of the data, and use that for solving problems? When you're happy with that, I'd like you to work on the mastery exercises, please.